Okay, so today we're going to talk about, we're continuing along in our discussion of turbulence and how we can model turbulence using our boundary layer equations, but they have to be modified. So today we're going to talk about this modified equation that we came up with last time, which I show up here. It's a little hard to see, so I'll zoom in, but this is our, I guess, our X momentum equation. And the whole classical statement of this is basically this section here, right? We're in this last term, we're including the viscosity or the viscous stress due to molecular diffusion, right? Mu is our viscosity, and that is giving us a proportion of diffusion of momentum due to the sort of intermolecular interactions. Okay, last time we went through and we derived this second term and figured out how it went into this equation. And this is now the turbulent mixing component of the viscous stress. So in the boundary layer, if we're really close to the wall, the viscous stress mu is going to dominate because the eddies are really small. As we get further away from the walls, we have more opportunity for eddies to form. That this molecular component starts to drop off, and we end up having really this as the only important thing. Right? And when I say that the mu part drops off, it's not actually changing, it's just becoming less important relative to the turbulent mixing. So this is great. We have these models here, but this u prime v prime, this whole integral, we don't really have, excuse me, we don't really have a way of modeling that yet. We don't have models that we could substitute in that give us some value of u prime and v prime, given the conditions in our problem. So what we're going to do today is talk through how we get to those models and what they look like, and some changes that we have to make in order to express the equations appropriately for those models. Okay, so let's kind of go through this a little bit. So if we start, we're saying here this term here that this viscous stress is the viscous stress. We'll just write it out. Viscous stress. Zoom on a little bit. Viscous stress due to molecular diffusion. Molecular diffusion, and that is right. That's this term here. This term here. This minus rho over t in the integral. This is Reynolds stress due to turbulent mixing. Turbulent mixing. Right? So we're clear on what both of those things are. It's clear that the first term, mu du dy, that is proportional to the gradient du dy, right? The contribution of the viscous stress due to molecular diffusion it's clear that that's proportional to the velocity gradient in y. But what you might not realize is that if you look at that second term, right, it doesn't look like that's proportional to that same gradient. It looks like it's just a function of u prime and v prime. But if you remember back, we decided that u prime and v prime are strongly correlated. And a disturbance in u prime leads to a negative response in d prime. And so it turns out, in fact, that second term is also proportional. And so that second term, this one here, is also proportional. That's proportional to the partial du bar dy, right? Because of the correlation between those two things. So what does that? How does that help us? Again, what we're trying to do is we want to get to models that we can use in place of this last term. So if we know that last term is proportional to du dy, then we don't have to. Then our model itself doesn't have to include that. We can develop a model of something that maybe multiplies this gradient instead. So we'll do that, and we'll call those constant of proportionality. Let's see. So let me write this out a little bit more clearly. So we're going to say this minus rho over t int, integral from 0 to t int of u prime v prime dt, right? That's proportional to some constant of proportionality, some model that we have that's going to multiply this gradient. And that's going to be, it turns out, rho times this epsilon sub m. Okay, this is going to be our density times the proportionality constant that we have to have a model for, times this gradient, which is du bar dy. Okay, so if we can go through and come up with a model for EM, we can have a pretty good approximation of that whole thing on the left-hand side. And once we have that, then we can have a model that gives us the equation, or it fulfills this equation for continuity in the boundary layer, in a turbulent boundary layer. Okay. So let's define this thing EM. So EM is defined as the eddy diffusivity of momentum. Okay. One thing that I do want to point out, though, is there is this correlation, right? There's this du dy, but if we look at the boundary layer velocity, so let's just sketch that out quick. So here we have, as a function of y on this axis, we have a velocity profile that looks like this on average. So as you get further out in the wall, the velocity starts to kind of level off. So very near to the wall, we said, if I have some fluid near to the wall and I disturb that in the positive y direction, I'm going to have a corresponding negative response in u, right? So v prime leads to a negative u prime. But this is only true if I've got a gradient, right? Like only right here next to the wall where I do actually have a gradient is a v prime disturbance going to lead to any change in u. Like what I'm saying is, what happens if I have a disturbance out here? Right? If I have a disturbance in this direction? Nothing happens because, okay, the fluid moves in y, but it doesn't necessarily lead to a corresponding change in u velocity. Okay, so this relationship, it depends on the gradient, the local gradient that's occurring in the boundary layer. So as we start, developing models for these, you're going to see basically two things, where you have some near wall thing happening, some velocity gradient you're accounting for near the wall, and then as you move out into the boundary layer, you have a different, it sort of takes over a different mode in the FID. Okay. Let's see. So moving on here. The same thing can be said of the energy equation, right? We just did this for momentum. For the energy equation, we have this term. This term here is our energy transport. Energy transport due to molecular diffusion. And that's going to be, well, it's just Fourier's law. So it's proportional to K, the molecular conductivity. And then the second term is our turbulent mixing term, right? So this is energy transport due to turbulent mixing. Again, the same thing applies. We have near the wall, very near the wall, where maybe in the viscous sublayer, the transport is going to be really driven by the molecular diffusion. As you get out and there's eddies forming, then it becomes small compared to that second term, which is the turbulent mixing term. Again, we can write this with a constant of proportionality. So we would say that second term, which is going to be rho c over t int, integral from 0 to t int of v prime t prime dt. That is, like the momentum was proportional to v prime u prime, this is proportional to, it's proportional to the gradient, right? V prime u prime is proportional to the gradient. This is proportional to the gradient of temperature with respect to position. So this is proportional to minus dt bar dy. And in fact, we can write it as the following. So we write it as minus rho C, our E sub H, right? So E sub H now refers to the diffusivity due to heat transfer, right? Or the heat diffusivity times dt, dt bar dy. So that's our model, and then our job then is to come up with good models for EH. Okay, so EH, let's just write this, or epsilon H is defined as the eddy diffusivity of heat transfer. All right, just really quickly, I could sketch what that looks like. Again, we have our temperature profile as we get away from the wall. Let's say this is our temperature. This is position Y. Right. So as we get away from the wall, and you have some change in V. Right, some change in V away from the wall is not going to lead to a change in T, but very near to the wall, a change in V does lead to a change in T. And so that's kind of how they're related to each other. Any questions on this so far? No? Okay. So let's kind of look at, I think conceptually, how do we maybe categorize the eddy diffusivity versus sort of molecular properties and come up with some maybe analogs for those things. So in the maybe momentum bucket here, we've got molecular viscosity, mu, right? That's going to be analogous to the turbulent viscosity, which is rho times epsilon sub m. So both perform kind of the same function in the equations. We have kinematic viscosity then, nu, right? Kinematic viscosity, which is equal to mu over rho, is going to be analogous to the turbulent viscosity, so rho is not changing as a function of the position of boundary layer, so it's just a property. So turbulent kinematic viscosity is then just equal to epsilon sub m. Right, so you can think of this epsilon sub m as the equivalent turbulent kinematic viscosity of the fluid. Okay, that's on one side. On the other side, on the energy side, we have our molecular conductivity K. Right, so K is going to be analogous to our turbulent conductivity. And that is rho times C times epsilon sub H. That's our turbulent conductivity. The molecular thermal diffusivity, right, which was alpha, which is K over rho C, is then analogous to epsilon sub H. Right, so again, you can think of epsilon sub H, our diffusivity in the turbulent region, as the equivalent of alpha in the molecular sense. All right, so let's look back at how to do this without writing too much. So if we look back at this equation, right, this is the original form of the equation. If we substitute in the models that we've defined here, we're saying now instead of rho c t int, the integral of v prime t prime, we substitute in the model that we're going to use for that. We can rewrite the equation as follows down here. So we rewrite this as, on the momentum side, it's just the same thing as it was before, which is rho du bar dt plus u bar dx plus v bar du bar dy is equal to minus dp infinity dx plus now d dy of, so mu plus rho epsilon m times this gradient d u bar dy. Right, that's our rewritten form using this model, and we'll next get to actually coming up with models for epsilon sub m. Okay, on the right-hand side, on the energy side, it's going to be similar, dt bar dt plus u bar dt bar dx plus v bar dt bar dy is equal to minus 1 over rho c times d dy of, let's see, minus k plus rho c epsilon h. And all of that is multiplied by dt bar dy. Okay. What did I do? dy here. So this needs a bracket. So yeah, so now we have this slightly more convenient form that we can work with, and we just need to get to the models. One thing I do want to point out, though, is we've made a distinction so far here between this epsilon m and this epsilon h. But so if we think about what's happening, epsilon m is going to be something like the kinematic viscosity. Epsilon h is something like the thermal diffusivity. Well, what is that, right? Prandtl is mu over alpha, right? So our Prandtl number is our molecular Prandtl number is that. These two things are equivalent in the turbulent regime. So actually our turbulent Prandtl number, PR turbulent, is equal to epsilon sub m divided by epsilon sub h. But okay, this is fine. But what do we know about the mechanisms of transport in turbulent flow? Right, for molecular properties in not turbulent flow, we could possibly have, like in the case of a metal, a liquid metal, you could have really good heat transfer properties and really poor momentum transfer properties. For turbulent flow, what is the thing that's dominating? It's movement, bulk movement of fluid. So you're really never going to have a situation where this Prandtl number is very far from 1. Both of those things are occurring by the same physical mechanisms. So this is always approximately 1. And in fact, in reality, it's actually closer to 0.9 for most fluids. So if we know this is true, we don't really have to worry too much about the Prandtl number, the turbulent Prandtl number. We can say that these two things, EM and EH, are the same model. We use the same model for both of them. It's just that maybe we have to scale one of them by a constant 0.9 or something like that. So in future slides here, what we'll do is develop these models, but only for one of the two components. We'll call it epsilon sub m. And then if we do apply it for the thermal boundary layer, there might be some scaling involved.